Hello everyone, welcome back to our channel gsipucmysuru. Today is the 8th session of our third chapter, that is Transistor Amplifier. In the last session, that is in the 7th session, we discussed about power amplifiers and its classifications. Classifications anta bandaga we saw 4 different types of classifications, that is class A, class B, class C and class AB. We are going to classify these amplifiers depending upon the location of Q point in the load line. If the Q point is present exactly at the center of the load line, then that type of amplifier is called as the class A type of amplifier. If the Q point is present on the cutoff region of the transistor characteristics, then it is called as the class B type of amplifiers. If the Q point is present above the cutoff region and just below the midpoint of the load line, then it is called as the class AB type of transistors. And if the Q point is present below the x-axis, then it is called as the class C type of transistor amplifier. Now let us begin this session with the comparison of all these types of power amplifiers. So comparison of power amplifiers. This is the table which I am going to use in order to compare all the 4 types of classes, that is class A, class B, class C and class AB for these 3 different parameters. That is, the very first parameter is conduction angle. So the conduction angle in the class A type of amplifier is the 360 degree. That is, the output is produced for the entire conduction angle of the input cycle. If the input cycle is like this, then the output of this class A amplifier is like this. I mean to say, all of the input cycle will be appearing across the output. So the same conduction angle when it comes to class B type of power amplifier, it is just 180 degree. That is, if the input signal is like this, then only 1/2 of the cycle will be appearing across the output. Either it can be the positive half cycle or the negative half cycle. It entirely depends upon the polarity of the signal what I am applying. Coming to class C type of amplifiers, the conduction angle is less than 180 degree. Less than 180 degree. That is, the cycle will be like this. Not full positive half cycle will be appearing. Only a small portion of the input cycle, only a small portion of one of the half cycle will be appearing across the output. Whereas coming to class AB, it is a combination of both class A and class B. So the conduction angle for this class AB type of power amplifier is greater than 180 degree and less than 360 degree. That is, more than half a cycle will be appearing but less than the entire cycle. That is, it will be something like this. Only more than 180 degree, that is, the entire positive half cycle is appearing, but in the negative half cycle a small portion will be distorted or a small portion will be eliminated. So the conduction angle in the class AB type of power amplifiers is more than 180 degree but less than 360 degree. Coming to this overall efficiency of this type of power amplifiers, it is very much poor in the class A type of power amplifier. Poor, about less than 50%. The efficiency, the overall efficiency of this class A type of power amplifier is less than 50%. Coming to this class B, the efficiency lies between 70% to 80%. And this class C type of amplifiers, that is class C type of power amplifier, more than 80%. Whereas in this class AB, it lies between these two, that is more than 50 and less than 70. So it lies between the range of 50% to 70%. So if you are going to look at this parameter, that is the overall efficiency, the efficiency of this power amplifier increases as and when the Q point is shifting away from the center of the load line. So similarly, the Q point will be located below the x-axis line. So if the Q point is shifted away from the center of the load line, then the efficiency of that type of power amplifier will increase. Coming to the signal distortion, in class A type of power amplifier, all of the input cycle is appearing across the output. So if the system is biased properly, there will be no distortion. If it is correctly biased. If it is correctly biased, then there will be no such distortion in the output signal. Coming to this class B type of power amplifiers, a portion of the input cycle will be completely eliminated. That is, one complete half cycle will be eliminated. So, one half cycle is distorted. Whereas coming to class C type of power amplifier, more distortion, because the majority of the input cycle will be distorted. Whereas coming to this class AB type of power amplifier, only a small portion of the input cycle will be removed. So, small distortion. So, this is the table which compares all the 4 different types of power amplifiers depending upon these parameters, that is conduction angle, overall efficiency and the signal distortion. Clear? Now we will move on to the next topic, that is class B push-pull amplifier. This is the circuit diagram which is required in order to construct this class B push-pull amplifier. In this circuit we are going to use 2 center tap transformers, that is T1 and T2, and 2 transistors Q1 and Q2. Here we are using NPN type of transistor. We can also use PNP type of transistors, provided this VCC source must be connected in the reverse direction. Why it is called as these T1 and T2 as the center tap transformer? Because from the center of the secondary winding we are going to take connections in both the type of these transformer. ಹಾಗಾಗಿ ಇದನ್ನ center tapped transformers ಅಂತ ಕರೀತೀವಿ. So for the primary winding of the transformer T1, we are going to give the input supply or the input signal which is sinusoidal in nature. And from the secondary side of this transformer, that is T1, we are going to connect Q1 and Q2. And for the secondary side of the transformer T2, we are going to give we are going to connect the load which is nothing but a speaker. And for the primary of this T2, we are going to connect the collector terminals of these 2 transistors. This is the base, emitter and the collector. Similarly, emitter, base and the collector. This center tap transformer is provided in order to generate 2 separate signals V1 and V2 which are opposite in polarity. Anta helidre, if V1 is like this, then V2 will be like this. There will be 180 degree phase shift between V1 and V2 in this particular circuit. So for T2 we are going to, that is for the secondary of the T2 we are going to connect the load, and for the primary of the T1 we are going to connect the input signal, or we are going to apply the input signal which will be denoted by Vin. In this particular circuit, both Q1 and Q2 are biased at cut off, which is done by providing the zero bias at the base terminals of these 2 transistors Q1 and Q2. How this zero bias is applied, or how this zero biasing condition is applied anta helidre, we are going to short the emitter terminals of both the transistors Q1 and Q2. Eradu emitter terminals na Q1 the transistor the emitter as well as the emitter of Q2 both will be shorted. and it will be given to the center tapped transformer T1. Again through this VCC it will be connected to the primary end of the center tap transformer T2. Now let us try to understand what happens for different half cycles when a positive half cycle is appearing across the input. Let us denote these two terminals as A and B. Since these transistors are nothing but two diodes which are connected back to back, as soon as the positive half cycle is appearing across the primary of this transformer T1, the voltage will be divided into two separate voltages, that is V1 and V2. So the polarity of the point A will become positive whereas B will become negative. Hagagi idu positive hagidrinda idu negative agutte. Since this is negative, this will become positive. And these are connected to the base terminal of these transistors Q1 and Q2. Since the polarity at point A is positive and that positive potential is connected to the base of the transistor Q1, only Q1 will start conducting, whereas Q2 ಆ Q2 ನಲ್ಲಿ ಬೇಸ್ಗೆ ನೆಗೆಟಿವ್ ಪೊಲಾರಿಟಿ ಕನೆಕ್ಟ್ ಆಗಿರೋದ್ರಿಂದ ಫಾರ್ ದ ಪಾಸಿಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ Q2 ವಿಲ್ ನಾಟ್ ಕಂಡಕ್ಟ್, ಓನ್ಲಿ Q1 ವಿಲ್ ಕಂಡಕ್ಟ್. ಸೊ Q1 ಕಂಡಕ್ಟ್ ಆಗಿರೋದ್ರಿಂದ ಇಲ್ಲಿ ದ ಎಂಟೈರ್ ಪಾಸಿಟಿವ್ ಹಾಫ್ ಸೈಕಲ್ ವಿಲ್ ಬಿ ಅಪಿಯರಿಂಗ್ ಟು ದ ಸೆಕೆಂಡರಿ ಆಫ್ ದಿಸ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ T2, ಬಟ್ ಇಟ್ ವಿಲ್ ಬಿ ಇನ್ ದ ಇನ್ವರ್ಟೆಡ್ ಫಾರ್ಮ್ and in the amplified form. So for the positive half cycle we are going to get the inverted version of the input cycle, which is amplified. Coming to this second half cycle, that is coming to the negative half cycle, avaga enagutte, this point A will become negative whereas point B will become positive, and accordingly even these two terminals will be interchanged. This becomes positive whereas this becomes negative. Since this negative polarity is connected to base, this will not conduct, whereas this Q2 will conduct, because for the base the positive polarity is connected. So Q2 will conduct whereas Q1 will not conduct. So for the negative half cycle Q1 will be in the off state or it will not be conducting, whereas Q2 will be conducting. So for the negative half cycle we will be getting an output across the load, but again it will be in the inverted form but in the amplified version. For the negative half cycle we are going to get a positive amplified version. For the positive half cycle at the input we are going to get the negative half cycle at the output. But even though these transistors are conducting alternatively, for the positive half cycle only Q1 will be conducting, for that I am going to get this output. For the negative half cycle only Q2 will be conducting, again I will be getting an output across the load. There will be the continuous output for this load, or there will be a continuous output to the speaker, that is the loudspeaker, even though for different half cycles is appearing across the input terminal of this transformer T1. So the input signal is applied across the primary of T1. So positive half cycle ಬೇರೆ negative half cycle ಬೇರೆ ಬೇರೆ ಬಂದ್ರೂ ಕೂಡ we will be getting the continuous signal at the output of this loudspeaker or at the output of this load ಅಂತ ಹೇಳ್ತೀವಿ. So the loudspeaker will receive the complete cycle of the amplified signal ಅಂತ ಹೇಳ್ತೀವಿ. So the efficiency of this class B push pull amplifier ಅಂತ ಬಂದಾಗ power efficiency is equal to P out, which is nothing but AC, divided by P in, which is nothing but DC. So this is the efficiency formula for this class B push pull amplifier. Clear? Now let us see another small topic, what is called as crossover distortion. So what is this crossover distortion? In the first year itself we have studied about the knee voltage present in the diode. Since this transistor is nothing but two diodes which are connected back to back, there will also be a voltage what is called as a knee voltage. The voltage at which the diode starts conducting will be denoted by Vk, that is nothing but the knee voltage anta ಹೇಳ್ತೀವಿ. Since this transistor is nothing but a connection of two diodes which are connected back to back, again there will be a small delay in the transition of signal from positive to negative or from negative to positive, because in each cycle of the input signal these diodes will conduct alternatively. So let's see that crossover distortion with the help of a waveform. This is the input cycle or the input signal what we are applying across the class B type of push-pull amplifiers. For this particular type of waveform, we are going to get an output which will be distorted to small extent. So how that distortion will occur? The transistor will not conduct all of a sudden when the input signal is applied. There will be a small time delay between the application of the input signal and the conduction of the transistor. That is all because of the knee voltage. So for silicon, the knee voltage is equal to 0.7 volts, and for germanium it is equal to 0.3 volts. So this dashed line is an indication of 0.7 volts or 0.3 volts depending upon which type of diode or which type of transistor I am using. So whenever there is the change over in the cycle from the positive to negative or from the negative to positive, there will be a small delay. So that delay can be represented like this. We are going to draw the dashed lines from these points, and in those points the output voltage will be 0. The diodes or the transistor will not be conducting in those time intervals, and this distortion which is appearing when the signal is crossing or when the signal is jumping from the positive half cycle to the negative half cycle or from the negative to positive itself is called as the crossover distortion. That is, at the time it is crossing the signal from the positive to negative or from the negative to positive, there is the distortion in the signal, and that distortion itself will be called as the crossover distortion. At that point, neither of the transistor will be conducting, and the resulting distortion itself is called as the crossover distortion. Clear? Now it's time to have a look on part 2 of the session. Hello everyone, welcome back to part 2 of the session. In this session, we are going to discuss about what is called as proximity sensors. It is nothing but a sensor able to detect the presence of nearby objects without any physical contact. A proximity sensor often emits an electromagnetic field or electromagnetic radiation, that too infrared radiation, and looks for the changes in the field or the return signal. The object being sensed is often referred to as the proximity sensor target. Different proximity sensor targets demand different sensors. Example, a capacitive proximity sensor or a photoelectric sensor might be suitable for a plastic target. An inductive proximity sensor always require a metal target. An ultrasonic sensor always require a glass, liquid or powder target. Sometimes these proximity sensors are also known as non-contact sensors because they don't require any physical contact with the object being sensed. Even our mobile phones will have proximity sensors. Our smartphone screen and touch screen is turned off to save battery life and unintentional operations. Now let us look for the applications of this proximity sensor. It is used to detect the presence of any object without any physical contact. The second important application is it is used to detect and measure any changes in the surrounding environment. It is also used in the home automation system, such as to turn on the light automatically when any person is present in the room. It is also used in object counting purpose in moving the conveyor belt. For example, in filling the juices for the glass container. Used in speed measurement, the direction of rotation measurement of electric motors, and also it is used to measure the speed and distance measurement purpose of vehicles. The same proximity sensors is used to measure the speed of vehicle such that the traffic police are going to use this proximity sensor in order to check the overspeed. Now let us see some of the advantages of proximity sensors. There is no mechanical part, that's why it has a long functional life and it is highly reliable. The cost of these proximity sensors are very low and is having a simple working principle, so it can be used in any kind of simple circuit. With this, let me conclude part 2 of the session. Thank you. So in this session we saw the comparison of all the 4 different types of power amplifier, that is class A, B, AB and class C type of power amplifiers. Apart from that, we also saw the class B push-pull amplifiers. With this, let me conclude this session at this point. I'll be coming soon with the next session. Until then, take care. Bye-bye.